Right, this is a worked paper, the CIE Additional Maths from February 2018, paper two, this one. So I'm just going to go through all the questions, and hopefully you will get something out of this. So here we go. Right, before going into the questions, perhaps I could there's just a couple of things in this sort of formula page that I think might be useful. The binomial theorem, first of all. So we've got the expansion of the binomial here. Now that's all well and good. I actually like to remember it in this form here. Um, I think this kind of works quite well because this is kind of all the terms are like this. So by way of example, if we wanted to expand 3 minus x over 2 to the power of 8, um, say we wanted to strip out the term in x cubed. So that would be the term in 3 to the power of 5. So basically our coefficient is 8 factorial, which of course is the power to which we're raising it. Then 5 factorial times 3 factorial. And those come about from these terms. So 3 to the power of 5 and minus x over 2 to the power of 3. Okay, so this is always Rn. These two add to n and are basically the same as these powers here. And these, of course, likewise will add to n, 8 in this case. So I think that's kind of quite a useful way of remembering it. Might help you, it may not do, but just try that. Second one is this identity here, this trig identity, which to some may appear that it's just sort of come out of nowhere, but actually there's kind of quite a nice way to derive this. If you can imagine, we've got the unit circle, we've got a point here, which this sort of point travels right right around the circle, but let's say it's got to this point here, and we're measuring this angle here between this is, let's take this as being the start line, don't we? So we're doing that angle there. So the sine of this angle theta here is going to be the opposite over the hypotenuse. And of course, the hypotenuse is 1. So therefore, this side is sine theta. Okay. So, and which is right because sine theta is always less than 1, isn't it? So that looks good. And then by a similar argument, that is cosine of theta there. So we now adopt the Pythagorean hypothesis, then it's we basically got sine squared theta plus cos squared theta equals 1 squared. And we get this. These two come about really by, well, if we just look at the definitions of secant, sec theta, it's just 1 over cos theta, and cosecant is 1 over sine theta. So these are basically derived by dividing this one through um, by either sine squared theta or cos squared theta. We don't see this version of it too much, but this one actually we do see quite a lot. Well, both of these we see a lot of these in various contexts. So that basically is how we get these identities. All right, so let's go on to question number one then. Okay, so set theory question. Write down the set represented by the shaded region. Well, it sort of kind of looks as if this has started life as being the union of P and Q. But of course, we've got this bit excluded, the bits that's in R. So in actual fact, this is the intersection of that P union Q with R complement, everything that's not in R. All right. So the bits that are not in R are obviously the bits that are outside of that circle. So that's how we get the shaded bit. Part B, it says basically complete the Venn diagram with all the elements of these rules here. And so which is what we've done there. It says write down the value of the number of items in A union B union C complement. So what's the number of items not in the union of those three sets? Well, clearly that's just that element. So the element is 9, and the number of elements is just the one. Right, okay, move along then. Okay, so this question, determine the set of values of k for which the equation that lot has no real roots. Okay, so this comes about as a result of well, when we think of the quadratic formula, and in particular this bit here, which we call the discriminant, then we've got three possibilities. If this is a positive number, then we're going to end up with uh, uh, two roots because we've got a plus and minus there, and we'll get one for each of those. If it is 0, then this whole thing just drops out, and our root is going to be just minus b over 2a. If, however, it's negative, then we can't solve this. And that corresponds to the situation where there are no real roots. That's no no roots in the real number set, which is the only one we're sort of interested in up to A level. Obviously, we do complex numbers if we're studying further maths and beyond, but as far as A level is concerned, no real roots basically means none in the real number system. So, all right. So, what are we going to do here? So, the no real roots it means this discriminant is less than 0. So, so that's in this case, that's giving us this inequality here. B squared minus 4ac is less than 0. So if we expand that and work that through, factorize it, there we're going to get this. Now we have to solve this quadratic inequality. Now, the nature of these things basically is we've got two things multiplied together that are less than 0. So therefore, one of them is negative and one is positive. All right, so we have to look at each case in turn. So let's look initially at this is positive and this one's negative. So that's going to give us 2k plus 1 is greater than 0. And 2k minus 3 is less than 0. So that's going to give us k is greater than a half from there, and k is less than 3 over 2 from there. Okay, that's okay. If we look at the other way around, the negative positive, we find that actually we end up with this k is less than a half and k is greater than 3 over 2. Well, we can't have that, can we? It can't be both less than minus a half and greater than 3 over 2. So that one is not it doesn't provide a solution to us, and we're just left with what we've got in the first one. So I've rewritten that there. K is between minus a half and 3 over 2, and that so any value of k in that range will render this as being a quadratic with no real roots. Right, okay, so that's that one. Let's go on to number 3. Oh, we've got a bit of an overlap going on here. Anyway, a group of 5 people consists of 2 women, Alice and Betty, and 3 men, Carl, David, and Ed, A, B, and C, D, E. 3 of these 5 people are chosen at random to be a chairperson, a treasurer, and a secretary. Find the number of ways in which this can be done if the chairperson and treasurer are both men. Okay, so this is a combinatorics problem. And very often with these things, when we're dealing with factorials, but more than often we have to break it down into a number of cases. And this part 1 here is one such situation. So we've got sort of 6 choices for the chair and treasurer using the initials of these people. We can have CD. So the first one here is the chair, and the second one is the treasurer. CD, that's Carl and David. CE, DE, DC, EC, and ED. So 6 different possibilities. Having chosen those two, we're left with three people: the remaining man and the two women, and we have to choose one of those for the secretary role. So there's obviously three different people to choose from. So within each of these, we've got three different possibilities. So therefore, the total number of different ways is going to be six there, times these three, giving us 18 ways. Okay. Um, Part two, these five people sit in a row of five chairs, find the number of different possible seating arrangements. If, first of all, David must sit in the middle. Right, David must sit in the middle. Okay, well, if he sits in the middle, then that's fairly straightforward because we've got four people to allocate to the four other chairs. So it's, sort of David's just not counting in this really. It could be the same if David was sitting at the end. It wouldn't really matter. But he's occupying that one. We've got this one, this one, this one, and this one to allocate to four people. So that's four different people could go into the first one, three into the second, two into, and then one. So 4 factorial, that's 24 ways. And then Alice and Carl must sit together. Okay, so we've got a number of different possibilities here. We can have A, C. We can have A, C. All right, okay. So and so on. So there's four different ways we can have positions. We can have A, C, but then we can also have C, A. Okay. Carl, C and Carl, and then Alice. So that's 8 altogether. Yeah, 8. We're just looking at which chairs Carl and Alice can sit in. If they are sitting together, then there's 8 ways. And then, of course, we've got 3 other people to place in the remaining 3. So for each of those 8, are going to be 3 factorial ways that we're arranging the others. So the total number of ways is 8 times the 3 factorial, which gives us 48 ways. Okay. Okay, so that's the combinatorics question. Right, this one basically on, well, transformations of graphs, essentially. State the amplitude of 15 sine 2x minus 5. Okay, well, I've drawn that one on here. And what do we mean by the amplitude? Well, basically, it's the distance from the mean line up to the top, and we've got to do the period as well. Well, the period is the full cycle of a sine wave, cosine curve, or any other repeating form. So now I've drawn this. So I've actually started off with the sine curve, and then we've done these transformations. First of all, rather than sine x, we've got sine 2x. That has the effect of squashing it up by halving the period. So it's not 360 anymore, it's 180. And then we've actually multiplied the whole thing by 15. So instead of going from -1 to +1, which is what our original sine curve would do, um, then it's going from well, -15 to +15. Of course, we've added we've done that, but this -5 doesn't really affect the amplitude. All it does is shift the whole thing up by 5. That 5, in fact. So the amplitude, therefore, has been multiplied up from 1 by 15. So it's therefore 15. So we've got 15 and 180. Part B. Okay, the diagram shows the graph of y equals the absolute value of some function between -180 and +180. Write down the 2 possible expressions for the trigonometrical function f of x. Well, I think about it, probably have to just spot that this starts life as being tangent curve. This is tan x here, I've got here. And if we were to take the absolute value, sometimes we use the term modulus, but term modulus is used for other things. So for this sort of thing, better to stick to the idea of absolute value. Um, okay, and in which case all the negative bits here get flipped up, reflected effectively in the x-axis. So we end up with that. All right, so that's one possibility. We got the other one is well, um, tan minus x. Now, this is a transformation of graphs. So if we're actually replacing our x by minus x, what we are doing is reflecting the whole curve in the y-axis. So I flip that over, and then of course, if we then take the absolute value of it, we're going to end up with the same thing, which is the graph we got over here. Right, so that's that. Those are the two possible solutions. I dare say there might be other things if we got really complicated with our maths, but those are the ones they're looking for, obviously. And state the number of solutions of the equation absolute value of f of x equals 1 over this interval. Right, we're drawing it here, and of course this line here is f of x equals 1, y equals 1 if you like. And so so the solution to this equation is where these lines cross. So looking in the interval from minus 180 to plus 180, that point, that point, that point, and that point, 4. 4. We're not asked to actually solve the equation here. We just asked for the number of solutions. Okay. Obviously, I've cheated when it comes to drawing the sketches on this. You would have to actually sort of draw it by hand. But anyway. Um, There we go. Right, number 5, a vectors problem, effectively, although it's not actually written as a vectors problem. A river is 104 meters wide and the current flows at 0.5 meters per second, as shown. A woman can swim at 1.6 meters in still water. That means she can sort of swim across there. She swims from point A and aims for point B directly opposite. You can see up there. But she's carried downstream to point C. Calculate the time it takes the woman to swim across the river and the distance downstream, BC, that she travels. Well, we're considering here the velocity, the velocity and the displacement in both directions. In vector terms, we often term this as the I direction, and then and that being the J direction, these being sort of those two, the positive directions as well, because we can go negative. Okay, so what we're interested um, in this problem is the vertical component of the whole problem. So in other words, the velocity and the distance. Well, I mean, that's basically just given to us on a plate, isn't it? So the vertical velocity is 1.6 meters per second, and the vertical distance is 104 meters. So the vertical time we just get from S equals VT. VT, if we can write that. Okay, so we're just calculating for t, and that's going to be equal to the distance divided by the velocity, 65 seconds. So she is swimming for 65 seconds to get from one bank to another. So we've just simplified that as being, the vertical part of the problem. Now we're going to think about the horizontal part of the problem. So again, we're going to apply the same formula. And in this case, we want the distance. So, but in this time, we've got the velocity that's given to us, and 65 is what we've just calculated before. So it's kind of her swim time is 65 seconds. Okay, so so S equals 0.5 times 65, 32.5 meters. So the distance from B to C is 32.5 meters. Okay, so we've just done that because we've split it into two perpendicular directions and calculated accordingly. Right, good. I hope that's okay. Let's have a look at this number 6 here. Um, Differentiate 1 plus tan x over 3 with respect to x. Probably just dip into some of the sort of background to this, what we're going to use. Well, first of all, this derivative here, um, you probably sort of do this not long after starting calculus. The derivative of tan x is sec squared x. Seems a bit odd, doesn't it? That this is a single power and this is a square. But remember, tan is actually sine and cosine. And in actual fact, if you were to use the quotient rule, this is the quotient rule here, the derivative of the quotient of functions, f of x and g of x, is this, the derivative of f times g minus f times the derivative of g, all divided by g squared. So if we did that on tan x, which is sine x over cosine x, this would be our f, this is our g, and we differentiate that through, we get 1 over cosine squared of x, which is secant squared of x. The other thing that we're interested in here is the chain rule. So if we've got a composite function g of f of x, then the derivative of g, effectively, with respect to x, which is the inside, right in the middle, is going to be dg df, the derivative of g with respect to f, times df dx. Right, okay. So what we got here is the derivative of this one. This is going to disappear pretty sharpish, isn't it? Just a constant. And then we've got the tan of, well, our g is tangent and our f is 1/3, right? Okay. So dg the GDF is going to give us this, and df dx is going to be the derivative of this inside thing, is going to give us 1/3. So because of this chain rule here, we're going to end up with this. Right, and then hence find the integral. Well, this is just the backward process, isn't it? So what we're saying is if um, if this is the if this is the derivative of this, then then this must be the integral of this. Just a couple of points to note. Then obviously, well, this is 1/3 of what we need, isn't it? So we need to multiply this by 3. Yeah. Okay. And you'll notice when you differentiate that, the 1/3 that's in the function here is going to multiply that and so cancel out. But the other thing is when we're integrating this, yeah, we're going to get our tan x by 3. But we've got to remember our constant of integration. All right. No, we don't necessarily know it was 1. We're integrating it. It's just going to be some constant. So we need to put that in when we integrate, obviously. Um, and then final line, I've just multiplied through by 3. So you might say, hang on a minute, are we not multiplying the c by 3? Well, we have, but 3c is just a constant anyway. So we can repurpose the letter c here. We don't really have to write 3c or change it to big C or anything else. It's just a constant. Okay, so that is the differentiation integration problem. Let's have a look at this. This is number 7. All to do with radian measure, really, and the thing that we're interested, or the main two things that we're interested in radian measure. And remember, radians, a full circle in radians is 2 pi. Obviously, in degrees, it's 360. But things being in radians, quite a lot of things work out a lot easier. Anyway, we've got these two formulas. The area of a sector, this is half r squared theta. That kind of works nicely. We would put 2 pi in there, then we're going to get areas pi r squared, which is what we know it to be. And the other one is the length of an arc, which is r theta. There's an arc there, and so the length of that would be the radius times this angle, if you know the angles in radians. And the other thing that we need on this particular problem is the area of a triangle, um, which is half AB sine C, isn't it? But if it's a circle, and we're looking at this kind of triangle here, then A and B are both the radius, so it's radius squared. Okay, so find angle theta, it says, first of all. So if we look at sector OAB here, we've got angle theta there, and radius of 8. So the well, it tells us that the area of sector AOB is 20, and so we're using this formula here. We know this, we know that, and we want to know that. Okay, so if we rearrange that, we just get that. So the angle theta is going to be 2 times the area 20 divided by the radius squared, 8 squared, and that simplifies to 5/8 radian. Good. Okay, and it says find the, what does it say? Find the length of arc AB. Okay, so AB is given by, the length of an arc is given by this formula. So quite simply, now we know what that is. We obviously know what that is. We can just compute this directly. L equals 8 times 5/8. So that's going to be 5 centimeters. That's that arc there. And then the last one, which is just off the screen here, is to find the area of the shaded segment here. Right, okay, well, this is going to be the area of the sector minus the area of the triangle. Okay, right, well, we can see from our formulas that we've got up here that the area of the sector is going to be this, the area of the triangle is going to be that. So if we plug in our numbers, yeah, half r squared with 32. This is 1.4, and sine of 1.4 we can look up. All right, so stick that into our calculator, and it's going to come up with 13.27 square centimeters to 2 decimal places. Very important to put your accuracy into your answer as well as your units, of course. Right, so that is that one. Number 8. Solve the following equations. Right, 5e 3 to the power of 3x plus 4 equals 14. So this is an example of an exponent log equation, and the challenge here is we've basically got our unknown well, it's in the exponent here. That's the power. But in general, if we've got something in the argument of a function, because we could write that as we could write this, couldn't we, as a, as a function. Then the way we'd do this is we would actually then apply the inverse function to each side of the equation once we've arranged it appropriately. So we are effectively doing that, which we then know to be that. That's from knowing about composite functions. Right, okay, so now we're not quite where we can do that. First thing we need to do is need to divide through by 5. So that's what we've done there. And then we can apply our inverse function. Well, the inverse function of exp is log. So if we log and it's the natural log, of course, because this is Euler's number. If we log both sides of this equation, we're going to get our argument here down on the subject line, exactly what we want. And this is just computable on the right-hand side. Okay, so if we rearrange that, we're just going to get this, and we can stick that in our calculator to get this answer here. Right, part two, the log is signified as LG here. That means it's log base anything. It doesn't matter for the purpose of this problem. Log of 2y minus 7 plus log of y equals 2 log 3. So, well, using one of our log identities, of course, that left-hand side is the same as this. And 2 log 3 is the same as log 3 squared. So now, well, you can sort of think we're exponentiating both sides. It doesn't really matter. We know if that argument of this log function is equal to this argument of this log function, then the two are the same. So we can just write like that. Rearrange that as just a quadratic equation that's going to come down to this factorization, and that's going to give us these two solutions, -1 or 2/9. Now we should note here that -1 isn't going to work. All right, it might be a solution to this quadratic equation, but it's not really a solution to our initial equation. And what we always need to do with our solutions is check them back in the equation, in the original equation, to make sure that they make sense and they work. We can check through if our values for y make the left-hand side equal the right-hand side, then it's a solution to the equation. So in this case, yeah, the -1 doesn't work, but the 2/9 that comes out of this factor here, that is a solution. Yeah, so that's the solution to this equation. It's y equals 2/9. And finally, this looks a bit nasty, but we've got to write this expression here as a single logarithm to base 2. Right, the numerator looks pretty straightforward, actually. Yeah, subtracting those two, so we just want the quotient of p and q, log base 2 of p divided by q. What about log base 2 of r times log base r of 2? Well, log base r of 2 in actual fact is this thing. Yeah. Okay. Now we can use our log rules to do that. We've got the rule that actually, sometimes we call it the fourth rule, that actually allows us to convert the put the numerator in the or put rep or kind of replace this with a quotient of log, say natural log of 2 divided by natural log of r, and if we do that, we basically end up with this. It's just the inverse, and therefore we get these cancels with that, and we're just going to end up with the numerator log base 2 of p over q. Okay, so that's kind of quite a nice one. Something to watch out for, I think. That fourth log rule that where we sort of can put different bases over the same base. Then it doesn't actually come up that much, but it's an important one. Right. Ooh, now this one, this is a bit of a beast, really. This one, not the first part, but the second part's a bit awkward. Okay, so coordinate geometry 1, P is the point 8,2 and Q is the point 11,6. Find the equation of the line L that passes through P and is perpendicular to the line PQ. All right, so I've got a sketch of it here, which makes it a lot easier. And well, as with all A-level maths in general, really, diagrams are really useful. Sometimes they're absolutely essential. And when you see my mechanics videos, you'll know I will go on at great lengths to tell you how important it is to draw your diagrams. Anyway, this is not mechanics, um, but this is what we've got. So these are the points here, P and Q. We've got those there, P and Q. So we've got this line here. And there is a line L which passes through it like that. Sure, it says L2, but that's line L. And we're going to be worried about point R in a moment, but we want to find the equation of this line in the first place. All right, so what we're using here is the fact that we can work out the gradient of this, which is 3/4. That's using the rise over the run, using that and that. So another gradient. Therefore, we know the gradient of this line because this is normal to it. It's perpendicular to it. And we know a point that it goes through. So we can work out the equation of L from this little formula, y minus 1 equals the gradient into x minus x1. And our x1 and y1 are going to be these here. This point here. That's what the one point we know on the line, one point we know at the moment. So if we substitute those in there, we're going to get this. I've noted this is 1 because we're going to use this in part 2. But we would normally write the equation like that. All right, so that's that one. And the second part, the point R lies on L such that the area of triangle PQR is 12.5 units. Showing all your working, find the coordinates of each of the two possible positions of point R. Well, of course, there are two triangles that we could form with PQ as a base. In this case, and that's one, and then the other one is down here. But I've just shown the point R being up here, and hopefully the solution for the other one will come out of the calculation. So this is just for diagrammatic purposes. All right, so, well, we're told that the area of this triangle is 12.5, so that's kind of not a lot of use unless we know uh, the lengths involved, really. Well, we can work out the length of this. Basically, we're using Pythagoras, PQ there, on these points, and that's going to give us a length of 5. So this length PQ here is 5. We wouldn't denote the length in these absolute value delimiters. So that's what we mean by that. The length of PQ is equal to 5. Right. We therefore can conclude from that that this length is also 5. Yeah. Because if we work out half base times height of this triangle, then in order to give us an area of 12.5, this would also have to be 5. Half of 5 times 5. All right, so we know that the length of PR is 5. Right, we just need to find the coordinates now. So if we let R equals xy, that's the coordinates of that point, the general coordinates. And then if we work out this length using Pythagoras, what have we got? We've got x minus 8 squared. All right, so that's x minus 8 all squared plus y minus 2 all squared. Yeah. Equals 5 squared. Right. We can't solve that on its own, but note that up here, this is why I sort of kept this form of the equation for L handy, because it's y minus 2, and we can substitute this right-hand side in there. And when we do that, we get this And then, well, so this is just a quadratic in x, and we can solve this. It's going to give us our two solutions, isn't it, for the two positions of R. Um, how do we do that? Well, multiply through by 16, complete the square, basically. Okay, you can, if you're not convinced, you can pause the video and just have a look at that. But that's essentially going to give us values of x of 4 and 12. And then we can go back to this equation for L and work out the values of y that go with these values of x. So when x equals 4, y equals 5, when x equals 12, y equals -1. So you can maybe see that. So in actual fact, I cheated. I knew what the I knew what the solution was when I drew the diagram. So there's your 4, 5. So nicely in the right places, and we've also got 12 -1 there. Okay, so that is your solution. Now, it has to be said that this part two is a bit of a messy thing to do. It's so easy to make mistakes on this kind of thing. Um, I think you kind of know you're in for a bit of work when you see this. And in general, of course, the marks allocated to the questions are a bit of a clue as to how easy or difficult they're going to be. We tend to find there's a lot of kind of working out with these kind of questions. You just have to stick with it, really. Obviously, 6 marks is 6 marks, so if you can score that, then that goes a long way towards your grades. Right, okay, we're going to move on to number 10. The function f is defined by this for all real values of x, for all real values of x. Here's our all real values of x, and there is the graph. All right, well, obviously it goes on in either direction. Explain with reference to the graph why f does not have an inverse. Well, the point with inverse is that for a function to have an inverse, it's got to be a one-to-one function. So one value of x gives us one value of y. Because when we invert it, then they obviously need the single y to map to each y to map to a single x. Now here for there are two values of x that give us the same value of y. So if we try and invert it, that's going to cause us a problem. So therefore, on this domain that's been defined, which is that, the whole lot, it doesn't have an inverse. However, come back to that in a moment. It asks us what f squared of x is. Well, that's simply the square of the function. So that's fairly straightforward. Function g is defined for x is greater than k, and it has an inverse. What could k be? Well, we're looking for a set of values where we're only going to get one value of y out for one value of x. And if we limit ourselves, just say this right-hand part here, then that will do that. So we're effectively not changing the function, we're just changing the domain. Could we use this part? Well, you could, except for the fact that the question does actually say x is greater than k, so we're pretty well forced into using the right-hand side. Right, and the last part says find the inverse of g. Now, in order to do this, in general, what we do is we basically change the subject to the formula, and that is really what we're doing when we're doing an inverse. So quite simply, if we let y equals, or g equals that, but y equals square root of 1 plus x squared, and we twizzle that round, x equals square root of y squared minus 1. We always write our functions, don't we, in terms of x? Well, it says the variable is x, so we have to write it as x. So it's that. Okay. So that's basically about functions and composite functions. Um, a little bit more than you'd be doing in an ordinary GCSE maths. Right, okay, so this now is question 11. Now, don't ask me what happened to A and B. It seems to have disappeared off the internet. But C, quite a good question on its own. So let's just have a look at this. So C, the function h is defined for all real values of x by h of x is equal to 4 e to the power of x plus 2. Sketch the graph. Right, okay. Well, when we sketch it, I mean, I've cheated here and I've done it on Desmos, but we're going to want to know some of the key. Well, we know what an exponential graph looks like, and basically, it looks pretty well like this, doesn't it? No, that's what we've got there. The only thing is, we've got a couple of little transformations going on. So first of all, what we're doing is we're scaling everything up, stretching it out by a factor of 4, stretching it upwards. So instead of crossing the y-axis at 1, which is where our sort of their exponentials will cross. This one's going to cross at 4. Well, it would do, except we're now going to shift it up by 2 as well. So we are actually crossing the axis at 6. It does say give the coordinates of any points where your graphs meet the coordinate axis. So really, I should actually mark on there that point there is going to be 0, 6. Okay, just added that in. All right. And on the same axis, sketch the graph of h is the inverse function of x. Right, well, as before, what we're going to do is we're going to change the subject to the formula. Let y equals this lot. And then we end up with this. And then, of course, what we do is we take the actual log of each side of the equation. That's the inverse function of that. And we end up with this. All right, so how would we sketch it? I mean, the simplest thing really is we basically just want a reflection. This is what functions and inverse functions do. They reflect in y equals x. If you're not convinced by that, just give it a little bit of thought as to you can probably find the intuition that goes behind it. Before I write down the point of intersection there, I want you to shout it out to yourself. Well, yeah, obviously it's going to be 6 along. Yeah. It doesn't graphs meet the coordinate axes. These are the only points. I mean, we might note the asymptotes as well. We have basically we've got this horizontal asymptote here, which arises from this because it's stretched up by 2. Okay, so that is 10C. Yeah, I'm sure 10A and 10B were very interesting, but we'll never know what they were. Right, trigonometrical identity here show that this lot equals the cotangent of A. So in order to do this, well, we're basically going to use our Pythagorean identity that is on the formula sheet, formula page at the beginning. If we multiply this out, which is the difference of 2 squares, we're going to get that divided by sine A cos A. Now this, if we rearrange our sine squared plus cos squared equals 1, this is going to give us that. So we've got cos squared A over sine A cos A. We can do some cancellation there. It's just going to leave us cosine of A divided by sine A, which is the cotangent. When we're dealing with identities, we can divide through by sine and cosine and stuff, and because this is something which is true for all values, so we're quite entitled to do that. If we are solving an equation, then we have slightly different rules, and we have to consider the zero case, but that's for another time. Right, okay, hence solve this equals a half. Well, of course, this is the cotangent of 3x. Yeah, so we're just basically using this this identity here to change this. So we got that. And you probably already know that whenever it says well, sometimes it says hence or otherwise. If it says hence or otherwise, it just means hence. There isn't an otherwise. So we're going to use this thing here. Okay. So how do you solve cotangent things? You can't really, because you don't have them on your calculator, or you might have them on your calculator, but you don't want to be using that. So we just twist this round, take the inverses. We've got tan 3x equals 2. Therefore, using the inverse tan, 3x is equal to this. Right. Now, the thing is that we know that actually we're going to divide through by 3. So there are going to be other solutions when we think of our periodicity of the tangent curve. Well, it repeats every 180 degrees, doesn't it? So we're going to have to include some other solutions, because when we divide through by 3, we're going to be finding things in the range that we are interested. All right, so not only does this equation yield that, but also that and that. And when we divide these 3 by 3, then we're going to get that, and that as our solutions. So again, if you were to plug x equals 21.15 into this equation, or this left-hand side, it will equal a half, and so on with the other. So it's a solution. Right, okay. Part B, solve this 10 tan squared y minus sec y minus 1 equals 0. We're in radians now. We've jumped into radians. Okay, so all right, we got this identity. Okay, so that's the identity that we had at in the formula page. And if we rearrange, we get that. So we can actually then, into our equation, we can then actually put that instead of the tan squared y. So that's a sort of fairly common use for this identity. Yeah, so we see that quite a lot. Right, and so yeah, just so we've now got a quadratic, haven't we, in secant of y. So we can work that through and come up with these two solutions. And then once we've got that, we can use our calculator. Well, we don't really need to use our calculator for cos y is minus 1. I mean, we know that is, we know that's going to be pi. But we use the calculator for this, and that's going to yield these results. Well, it's going to yield that result, because we're now looking between 0 and 2 pi radians. So we're going to be looking at that 2 pi minus this primary. I've also included this is actually kind of also another solution. Again, using the the periodicity. So yeah, 2 pi minus 0.43. Oh, sorry, that is 2 pi minus 0.43. That's what I mean to say. Um, so we've got the three solutions. Primary solution, this is 2 pi minus the primary solution, and this is pi that comes out of that value there. So we've got our three solutions in the range of 0 to 2 pi. Okay. Yep. So that I should have a little, should say equals 5.85. So that's what we had, and we calculated it to 5.85. Right. Okay. So I hope that helps. And so this is the final question, I think. This is the final question. Finally getting there. Now these are interesting. There's a calculus problem with this with three variables. And with three variables. So we have to kind of operate a bit of substitution. And we're also applying the chain rule to this as well. All right. So the volume and surface area of a sphere are given by that. Standard formulas. The volume of a sphere increases at a rate of 200 cubic centimeters per second. At the instant when the radius of the sphere is 10 centimeters, find the rate of increase of the radius of the sphere. All right. So we are looking at the rate of increase of the radius of the sphere. That is dr dt. All right. So we're going to apply the chain rule here because we don't know dr dt. It's not given to us here, but we can derive it from, well, dr dv times dv dt. We're given dv dt. We know we're given that because that's 200. Dv dr, well, basically that's the derivative of the volume function. And dr dv is just the inverse of that. Yeah, so the reciprocal, I should say. So if we flip that over, that being 4 pi r squared, and put it on the denominator, then that is that. It looks like a sleight of hand, doesn't it? But these things, these are real ratios. I mean, they might be functions, but they're still ratios. Yeah. And what they're saying is, they're describing the function that defines an infinitesimally small change in these quantities. So we're quite entitled to do like this. So this is kind of what we're doing. It's sort of reverse cancellation, isn't it? We're actually sort of putting extra things in here because we know that those are the same thing. So that's going to give us this. That's the 200 from there and the 4 pi r squared from there. And that simplifies to that. Well, it's at the so that is the general rule, but we're told that we want the rate of increase when the radius is 10 centimeters. Okay, so we can substitute r equals 10 in there, and we're going to get that figure. And then finally there, the rate of increase of the surface area of the sphere. Well, similar thing really. We want ds dt, and we can derive that from ds dr times dr dt. Okay. Well, we know what dr dt is now because we've just calculated it. It's actually that. ds dr is the derivative of s from there. So that's going to be 8 pi r. That's just using the power rule. So 8 pi r times 50 over pi r squared is going to give us that. Again, we're doing both of these parts when the radius of the sphere is 10. So it's 400 over 10, 40 square centimeters per second. Right, we've finally got to the end of the paper. Flown through it a little bit, um, but I hope you found that interesting and useful. You can rewind and go over things and pause and look at the working out if you choose to. Um, but anyway, we've done that, and I'll see you next time.